So here, I'm going to answer this momentum question that you can see. Where it says, the diagram shows a gas particle about to collide elastically with a wall. Which diagram shows the correct change in momentum that occurs during a collision? So, diagrams are always helpful here. We've got a wall, we've got a gas particle that is heading off in this direction, and it's going to collide with that wall. The particle has mass m, it's moving at velocity v. Now, what that means is we can describe its momentum before it collides with the wall as a vector that points roughly in that direction, and the size of the magnitude of that vector is m multiplied by v. Now, what's going to happen is it's going to carry on moving in that direction, it's going to collide with the wall, and it's going to bounce off it, and it's going to move off in that direction. Now, it says in the question, it clearly states that it's an elastic collision. Now, what that means is we're not going to lose any kinetic energy. So, the particle after this is still going to have mass m, and because we're not losing any kinetic energy, it will still have velocity v. So the momentum after the collision we can represent by a vector that goes up in that direction and also has size mv. So the size of those arrows is the same, and they're making the same angle with the wall. It's not spinning off or doing anything like that. It's a perfect reflection, as it were. So the angle that they've given us is this one here, which they've called theta, which means that this same angle up here is also theta. That will be important later. Now, what they're asking us to do, which diagram shows the correct change in momentum that occurs during the collision? So, to find the change, we know that the momentum after the collision is going to be equal to the momentum before the collision plus the change in momentum. So in order to find the change, we need to do the momentum after minus the momentum before, and that will be equal to the change. Now, the momentum after is this arrow here. It goes up like that. Now, the momentum before is this arrow that looks like that, but we're not adding it. If we were adding it, then we could do a tip-to-tail diagram where we could draw the tail of this vector with the tip of that one, and it would go up in that direction. But we're not adding it. We're finding the difference. So we are adding it multiplied by -1. And if you're multiplying it by -1, you're reversing the direction of that vector. So we're adding on the reversed direction of this momentum. That's what you do when you find the difference. So actually, what we'll end up doing is having another vector that looks like this. So that is the momentum after. This is us taking away the momentum from before. And you can think of it, if we're adding it on, it goes in that direction. So if we're taking it away, it needs to go back in this direction. And so you can clearly see that the change in momentum is equal to the combined effect of these two vectors, which is one that looks like that. And that is option B. Just to clarify something I said earlier, when you look at the diagram, it shows you that angle of collision that the particle is making with the wall. And I said that it was important that the same it comes off at the same angle afterwards. That allows you to be sure that the change in momentum is a completely horizontal line. Now, none of the options, A or B, they're both horizontal, so you didn't have to worry about that. But if you were just asked to draw what the change in momentum looked like, the fact that those angles were the same as each other allows you to be sure that the change in momentum is a completely horizontal vector.